In this video, I want to show you how to use this equation to calculate the delta H reaction for a chemical reaction using the bond energies in the molecules that are reacting and formed. So for example, when acetone undergoes hydrogenation, it is converted to rubbing alcohol. We're going to use bond enthalpies to determine the delta H reaction using the equation above. What we're first going to do is determine the net amount of bonds that are broken. The bonds that are broken are bonds in the reactants. And then determine which bonds are formed, which are in the product. And then determine the net difference in the bonds. And why are we doing that? Because look at what's going on here in this equation. You're subtracting the bond energies that are formed from the bond energies that are broken. So if there's common bonds between the reactants and the products, those values of bond energies will subtract out. So we're going to look for differences in the bonding between the reactants and the products. So here are Lewis structures of the reactants and then the product. It is very important that you first approach this problem with correct, coherent Lewis structures. So if we look at this reactant molecule and compare it to the product, we see that this group of carbon and hydrogens on one side of the C double bond O and this group of carbon and hydrogens on the other side, they are identical to these two groups sort of on the sides of this molecule. So we could say that these two, we'll call them CH3 groups, will cancel out with these two CH3 groups. So we don't need to be concerned about looking up the bond energy for a CH bond and multiplying that by 6 and then subtracting the exact same number because that's what we have on the right side. So we could ignore those bonds. What we're looking for are sort of the unique bonds between the reactants and the products. So here's a C double bond O, and that C double bond O does not exist on the right side or in the product. So we need to consider the bond energy for C double bond O. We also need to consider the bond energy for a hydrogen to hydrogen single bond. Now on the right side, what's unique here? Well, there's one CH bond that we have to consider, and then one CO bond, and then one OH bond. Okay? So that's the tally of bonds we need to consider. Again, C double bond O, HH, one CH bond, CO, and then an OH bond. Here's a table listing the bonds and the associated bond energies. The bond energies are in kilojoules per mole of bond. And if we look back at that equation, we see that there's 1 mole of acetone and 1 mole of hydrogen and 1 mole of product produced. And within each of the moles, there's 1 mole of C double bond O, 1 mole of HH, 1 mole of CH, 1 mole of CO, and 1 mole of OH. So we have that considered in this table, 1 mole of each of these bonds. The bond energies are always positive because this is the amount of energy needed to break this bond. So we substitute these values into the equation, and I'm emphasizing multiplying 1 mole times 741 for 1 mole of C double bond O. The mole units cancel, and we're left with the unit of kilojoule. So in this particular problem, it's pretty easy in that set up the equation, put in the values, sum them up on both sides, and then subtract their sums. And the answer is negative 52 kilojoules. In this example, we're going to calculate the enthalpy change for the decomposition of hydrogen peroxide. We draw coherent Lewis structures for the reactants and products. So the bonds broken are the OH and the OO bond in the hydrogen peroxide molecule. Now breaking this molecule down and considering, this is important, the 2 moles of molecules, we have 4 HO or OH bonds. Where's that coming from? Each molecule has 1, 2 HO or OH bonds. So each molecule has 2, and then we have 2 molecules or 2 moles. So that's where the 4 comes from. And then we have 2 OO bonds because we have 2 molecules or 2 moles. And then now we take a look at the bonds formed. 2 water molecules and 1 oxygen molecule. Well, in the 2 water molecules, there's 4 OH or HO bonds. There's one and there's the other. So each water molecule has 2 OH bonds. And then we multiply that by 2 because of the 2 moles in the chemical equation. So that means we have 4 OH bonds, and those 4 OH bonds will cancel with the 4 OH bonds in the peroxide. So what's left? The elemental oxygen bond, which is an oxygen double bonded to oxygen. So the net, as far as bonds broken, we have 2 O bonds, which is a single bond, and then 1 OO bond, which is a double bond. So we set up the table, and we note that in the table, looking up the bond energies, 140 and 498. And now we substitute those values, also considering the mole values of the bonds. Okay, so there's 2 moles, that's where this 2 comes from, of the O single bond O, which is a bond broken, okay, right up here. And then we subtract from that the 1 mole of bond formed, which is a double bond that is formed from the oxygen, the elemental oxygen. And again, the mole units cancel, and you're left with the unit of kilojoules.